Avengers Endgame or Avengers Sword is out now. But don't think that I am gonna discuss about Avengers Endgame. It's your wrong. I am gonna discussing about the magnetic effect of electric current. So let us start today's topic. Magnetism. This term is quite familiar, and magnets? You all have played with magnets, and you know that magnets have North Pole and South Pole, and this is an example of a bar magnet. It's north and this is south, and we know that putting another magnet with North Pole and South Pole, these are two like poles, that as I have discussed in my earlier videos, this is North Pole, this is North Pole, and they are like poles, and this will go away, push each other. And if these are unlike pole, like this is north and south and this is south and north, they will attract each other. These are some basics and you have learnt it in class. So the question arises, how electricity can turn into magnetism. And the person giving the relation between electricity and magnetism is Ørsted. Remember it. He is a famous scientist, Ørsted, and he discovers suddenly and surprisingly, when he was in his experimental table, he had a magnet with the North Pole here and it is South Pole here, and he had by chance put a wire over here connected to a battery. So here we know, and we came to know, or otherwise you can say that he saw that this wire got deflected from its place, it moved away. So of course there is something that is affecting this, and from there we concluded that electricity also produces a magnetic field around it. Magnetic field is a region around a magnetic substance. It can be bar magnet or horse magnet, anything. Magnetic field is a region. It's a region around a magnetic substance under or in the field we can feel the influence of the magnetic substance. Either it will attract or it will push us away or something like that. We can feel it. Oh, not with our hands, something with other substances. Like if we put an iron nail over here, it will be getting attracted. This is a field. But if we put a nail over here, no, it's not gonna be attracted toward this, because it is out of this field. This field ends here. But if we put it here, it will be got attracted. So from there, Ørsted concluded that a wire carrying current also produces a magnetic field around it. And this field has a direction. So magnetic fields are a vector quantity. So we denote magnetic field with B. B is also magnetic intensity, and this is velocity sign. Sorry, it's not velocity sign, it's vector sign. Velocity is this one and speed is this one. Speed is scalar and this is vector, as it has both the magnitude and the direction. So you know that speed is a scalar, but vector quantity is velocity. So we have a direction of magnetic field intensity, magnetic field, and the magnetic lines. And oh, what are magnetic lines? You have seen I have drawn a line over here. These are not lines in actual reality. These are something we have imagined. So, these are the imaginary lines in a magnetic field depicting the magnetic field, and if we draw a tangent at a point to the magnetic field line, we will get the direction of the magnetic field at that point. So this is a wire, and we know that the direction is this way. So we draw a tangent over here. So the direction at this point is toward this way. And it can be also determined if we take a bar magnet and put a compass over here. It will denote over there. Then put it here, there, and put it here, there, put it here, there. And in this way, if we join the dots and the lines, then we will get a circular. They're closed, you can't see it, but if we look inside it, it goes from the North Pole to the South Pole outside, and then again from the South Pole to North Pole. These are totally closed. So inside the bar magnet, it moves from south to north, and outside it moves from north to south. So if we break a magnet, it can be also proved. If we break a magnet, it will not give separate poles, north and south, but it will have two different segments with south here, north there, south here. And so, as we know that the magnetic field line starts from north and goes towards the south, if we take it in this way, as from the earlier one, let us take that whole piece and consider it a whole piece. So it will start from north to south here, and we know that it moves from north to south. So here to here, here to here, here to here, and again from here to here and here to here. So what are we getting? We are getting that inside it moves from here to here. So the direction inside the magnet is here. Okay, it is clear. I have a tip for every student that one should always have a stimulations. You can get online stimulations that are very useful for understanding physics topics. It would be very easier. Some are European agencies we are getting. From the stimulations you can do various experiments, as it is impossible for getting a whole physics lab in your home. It's impossible. So what is possible? Getting a physics stimulations or you are playing stimulation game like plane simulation, Europa simulation, and just like that there are physics stimulations. Search for it and go for it. They are very helpful, and you are getting practical knowledges over there. And by putting a wire in a field of magnet, as I told Oersted experiment, let there be two bar magnets. So here is north and here is south, then the magnetic field lines will be here. So the field is gonna here. And let the current, let this be a closed circuit. This is a closed circuit, and we have mainly 2 points. And the current flowing from positive to negative. I is flowing here, so I is over there. And we know that the wire experiences a force. So in which direction? The questions come in which direction. As force is a vector quantity, in which direction the force is there. As we know that force is equal to mass into acceleration, and acceleration is equal to velocity by time, as velocity is a vector quantity. So acceleration is also a vector quantity, and we are multiplying it. So force is also a vector quantity. We are having force a vector quantity. We want to know what's the direction, and for finding that we have a rule. It's Fleming's left hand rule. And sometime in exam it asks for writing the Fleming's left hand rule, but simply write, stretch your hands in such a way that 3 fingers are perpendicular to each other, the thumb, the index finger and the middle finger. And in this way, first this finger, the index finger, should show the direction of the magnetic field, it's over here. And then the middle finger shows the direction of the current over here, it's gonna that way. And we have to put a matter that this will be the hand, and it's showing that the wire is experiences force downwards, so the force is downwards, it's downwards. Okay, another thing, to determine the direction of the field lines along a straight conductor, it is a straight conductor, not a coil. So there is a rule named right hand thumb rule, or say the Maxwell's corkscrew rule, and it works over here like this. If imagine holding a conductor such that the thumb indicating the direction of the current, then the curl of the fingers will indicate the direction of the magnetic field, and over here it's like that. It is two dimensions, so thinking it is very hard. Like if the current is going through this pen and it's going inside from this backside and going out from this tip, so holding this is this like this, and we are having the coil around this, means the coil are revolving in this way. Okay, sometimes it says to determine it. And one thing, when electron is moving, E minus, it's E minus, when E minus, electron is moving, the current flow is opposite. As I told, current flow is the flow of positive ions. And if proton, or say helium double plus, alpha particles move in a way, the current is in the same way. If it is moving over there, the current is also there, and if it is moving there, the current is there. Okay, sometimes it's asked in various books question, you are getting it in NCERT. And now we are very few topics left, and it will be covered in my next episode. Thank you and have a nice day. Please like, share and subscribe. If you like, please like. Going to do the next part in my next video. And thank you for listening it with patience, and I will upload it shortly the next episode.